Hello, and welcome to another gentle journey into the quiet wonders of our universe with Desire Sleep Stories. Tonight, we're going to drift together through the most relaxing facts about black holes and the gentle curves of space-time, all spoken with the kind of calm that lets your mind unwind and your body settle deeper into rest. There is no rush here. No need to follow every word if you feel yourself beginning to float away. Just breathe in slowly, breathe out even more slowly, and let these ideas wash over you like the softest light from distant stars. We are here together in this peaceful space, exploring science not to excite the mind, but to soothe it, to let facts unfold like slow waves on a quiet sea, carrying you towards sleep whenever you are ready. Let us begin at the very foundation with the idea of space-time itself, that vast and gentle fabric that holds everything we know. Imagine, if you will, a place where space and time are not separate things, but woven together into one seamless whole. In our everyday lives, we might think of space as the empty room around us and time as the steady tick of a clock. But in the grand quiet of the cosmos, they are partners, moving together in 4 dimensions that curve and flow in response to the presence of matter and energy. This idea comes from the careful work of Albert Einstein in the early years of the 20th century, when he realized that gravity is not some invisible force pulling things together the way we once imagined. Instead, gravity is the gentle curving of space-time caused by mass and energy, and objects simply follow the natural paths, the geodesics, that this curvature creates. It is as peaceful as a leaf drifting along the current of a slow river. The leaf does not fight the water, it follows the shape the water has taken. So too do planets orbit stars. Stars move through galaxies, and light itself bends ever so slightly when it passes near something massive. There is a profound calm in this picture, a sense that the universe is not chaotic but harmoniously shaped by its own quiet rules. To understand this curvature more deeply, let us linger here a while and picture it in our minds. Suppose we take a very large, very flat sheet, perfectly smooth and stretched out as far as the eye can see. If we place a small marble on it, the sheet barely notices. The marble sits there almost without disturbing anything around it. But if we place a heavy bowling ball in the center, the sheet dips and stretches downward, forming a gentle bowl shape that grows wider and shallower as it spreads outward. Now roll another small marble nearby. It will naturally curve toward the bowling ball, not because the ball is reaching out and yanking it, but because the path it wants to follow, the straightest possible path in this curved space, leads it in a circle or spiral around the heavier object. This is a simplified 2-dimensional picture of what happens in 4 dimensions with space-time. The Sun, with its enormous mass of about 1.99 times 10 to the 30th kilograms, creates a broad, shallow curve in space-time that keeps Earth and the other planets tracing their steady, elliptical orbits year after year. The curve is so gentle at our distance that we barely feel it as anything more than the familiar pull we call gravity. Yet it is always there, shaping the motion of everything around our star in the most unhurried, inevitable way. Einstein's insight did not come overnight. He spent years refining his thoughts, building on the work of earlier scientists who had glimpsed parts of the puzzle. Isaac Newton had given us a beautiful description of gravity as a force acting at a distance, and that description served us well for centuries, explaining the fall of apples and the paths of comets with remarkable accuracy. But Newton's view left questions unanswered, especially when light was considered. Light, we now know, travels at a constant speed of about 300,000 kilometers per second in empty space, and it should not be affected by gravity in the old Newtonian sense. Yet observation showed that light does bend when it passes near the sun, a fact confirmed during solar eclipses when stars behind the sun appeared shifted in their positions. Einstein's general theory of relativity, completed in 1915, explained this bending not as a force on light, but as light following a straight path through curved space-time. The sun's mass creates that curve, and light, with no mass of its own to speak of in this context, still responds to the geometry. It is a beautiful, quiet truth. Everything travels along the gentlest possible paths shaped by the universe around it. As we sit with this idea a little longer, let us consider the equivalence principle, one of the cornerstones that makes general relativity feel so intuitively peaceful. Imagine you're in a small, windowless elevator far out in space, floating weightlessly because there is no gravity acting on you. You feel perfectly at rest, drifting. Now, suppose the elevator begins to accelerate upward at a steady rate, exactly 9.8 meters per second squared, the same rate at which things fall on Earth. Inside the elevator, you would suddenly feel pressed against the floor, exactly as if you were standing on the surface of our planet. A dropped ball would appear to fall toward the floor at that same familiar rate. From your perspective inside, there is no way to tell whether you are experiencing true gravity or simply acceleration. This equivalence, Einstein realized, means that gravity and acceleration are two descriptions of the same gentle phenomenon. The curvature of space-time is what we feel as gravity, and it is indistinguishable from the curvature we would experience in an accelerating frame. There is a deep serenity in knowing that the laws of physics remain consistent no matter how we look at them. The universe does not play tricks. It simply reveals the same underlying harmony from every angle. Now, with this foundation laid softly before us, let us turn our attention to the places where space-time curves most dramatically, where the gentle dip becomes an inescapable well. These are the regions we call black holes, though the name itself came much later. The first mathematical hint of such objects appeared in 1916, when the German physicist Karl Schwarzschild, while serving in the army during the First World War, found an exact solution to Einstein's field equations for a non-rotating, perfectly spherical mass. His solution described a point of extreme curvature where, if enough mass were compressed into a small enough volume, the escape velocity would reach the speed of light itself. Nothing, not even light, could climb out of that well. The radius at which this happens is now known as the Schwarzschild radius, and it is given by a simple yet profound formula. 2 times the gravitational constant, g, times the mass, m, all divided by the speed of light, c squared. For our Sun, with its mass of roughly 1.99 times 10 to the 30th kilograms, this radius works out to about 2.95 kilometers. If the Sun was somehow compressed into a sphere only 3 kilometers across, it would become a black hole. The Earth, far less massive at 5.97 times 10 to the 24th kilograms, would have a Schwarzschild radius of only about 8.87 millimeters, smaller than the width of your little finger. These numbers are astonishing when we pause to consider them, yet they are exact predictions from the theory, verified in countless ways through observation and calculation. Let us linger on the Schwarzschild radius for a moment and imagine what it means in the quiet vastness of space. For a star much more massive than our Sun, say 20 times the Sun's mass, the Schwarzschild radius would be around 60 kilometers. If that star exhausted its nuclear fuel and could no longer support itself against its own gravity, the core would collapse inward, faster and faster, until it crossed that critical boundary. From the outside, an observer watching this process would see the star's surface appear to slow down as it approached the radius, the light growing redder and dimmer because of gravitational redshift. Time itself, as measured by a distant clock, would seem to stretch out indefinitely. The star would never quite finish its collapse in the eyes of someone far away. Yet for someone falling along with the star, the journey inward would feel finite and continuous, though increasingly strange. This difference in perspectives is one of the most peaceful paradoxes of relativity. The universe looks different depending on where you stand, but every view is valid within its own frame. Once the collapsing object passes the Schwarzschild radius, it forms what we call the event horizon, a surface that is not a physical barrier, but a boundary in space-time beyond which no information or light can reach the outside universe. It is like the point of no return on a river that flows so steeply downward that not even the fastest current can push a message back upstream. The event horizon for a non-rotating black hole is perfectly spherical and has no hair, as physicists sometimes say, meaning it carries only the information of the total mass, charge, and angular momentum that formed it. Everything else about the original star, its chemical composition, its shape, its history, becomes irrelevant once the horizon forms. This no-hair theorem, developed through the work of many scientists, including John Wheeler in the 1960s and 70s, tells us that black holes are among the simplest objects in the universe, described completely by just 3 numbers. There is a quiet elegance in that simplicity, a reminder that even in the most extreme regions of space-time, nature reduces complexity to its most essential form. Inside the event horizon, the curvature grows stronger, leading eventually to a central singularity, where the equations of general relativity break down and densities become infinite. We must be careful here, and note that what happens exactly at the singularity remains beyond our current ability to describe fully. It is a place where quantum effects, which we do not yet fully understand, in combination with gravity, would likely become important. General relativity predicts a point of infinite curvature, but most physicists believe a more complete theory of quantum gravity will smooth this out into something finite, though we do not yet know the details. For now, we can rest in the knowledge that the singularity is hidden from the outside universe by the event horizon, protected by what is sometimes called cosmic censorship. The universe, it seems, keeps its most extreme secrets tucked away where they cannot disturb the peaceful flow of events we can observe. Our journey would not be complete without considering that not all black holes are perfectly still and non-rotating. In 1963, the New Zealand mathematician Roy Kerr found a solution for rotating black holes, which is far more realistic because almost everything in the cosmos spins. A Kerr black hole has 2 horizons, an outer event horizon and an inner one, with an ergosphere in between, where space-time itself is dragged along by the rotation in a process called frame dragging. If you were to hover near the ergosphere, you would feel yourself being pulled into a spin even if you were trying to remain perfectly still. The rotation creates a region where objects can, in theory, extract energy from the black hole's spin by carefully slingshotting around it, though of course this is a theoretical possibility we observe only indirectly through the behavior of accretion disks. The gentle twisting of space-time in the Kerr metric adds another layer of calm complexity, showing us that the universe's curvature can have a swirling, almost hypnotic quality, like the slow eddy of a deep, quiet pool. Now, let us turn our attention to how these remarkable objects come into being through the long, unhurried lives and deaths of stars. Most stars, like our Sun, will live for billions of years, fusing hydrogen into helium in their cores and gently balancing the outward pressure of that fusion against the inward pull of gravity. When a star runs low on fuel, it expands into a red giant, sheds its outer layers, and leaves behind a white dwarf core that slowly cools over trillions of years. But for stars born with more than about 8 times the mass of the Sun, the story is different. These massive stars burn through their fuel much more quickly, often in only a few million years, because their cores are hotter and the fusion reactions run faster. When the core runs out of fuel, it can no longer resist gravity, and the star collapses in on itself in a spectacular yet ultimately quiet event known as a core collapse supernova. For the very heaviest stars, above about 20 or 30 solar masses, the collapse may not even produce a visible supernova. The star simply implodes directly into a black hole without much outward explosion. This process was first modelled in detail by J. Robert Oppenheimer and Hartland Snyder in 1939, using the equations of general relativity to show how a pressureless sphere of dust would collapse inward, forming an event horizon in finite time for an observer falling with the material, though appearing frozen from afar. Their work was a quiet mathematical prophecy of what we now observe as stellar mass black holes, objects with masses between about 5 and 100 times that of the Sun. Stellar mass black holes are the most common type we have detected so far, often found in binary systems where they pull material from a companion star, forming bright accretion disks that glow in X-rays as the gas spirals inward and heats up through friction. One famous example is the system Cygnus X1, located about 6,000 light-years from Earth, where a black hole of roughly 21 solar masses is steadily drawing matter from a massive blue supergiant companion. The material forms a disk that reaches temperatures of millions of degrees, emitting X-rays that we have studied for decades, with satellites like the Chandra X-ray Observatory. These systems remind us that even in the most extreme environments, matter finds a way to orbit and glow before crossing the horizon, giving us gentle windows into processes we could never see directly. Beyond stellar mass black holes, the universe holds far larger ones, the supermassive variety that sit at the centers of most large galaxies, including our own Milky Way. Sagittarius A star, at the heart of our galaxy, has a mass of approximately 4.3 million times that of the Sun and a Schwarzschild radius of about 12.7 million kilometers, or roughly 0.08 astronomical units. To put that in perspective, if we placed Sagittarius A star at the center of our solar system, its event horizon would lie between the orbits of Mercury and Venus, yet its gravitational influence extends far beyond, shaping the orbits of stars that whip around it at thousands of kilometers per second. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing a bright ring of glowing plasma surrounding a dark central shadow, exactly as general relativity predicts. The ring is about 50 microarcseconds across, a tiny angle that required a global network of radio telescopes working together as one Earth-sized instrument to resolve. The image is not a photograph in the usual sense, but a reconstruction from radio waves. Yet, it is one of the most peaceful confirmations of theory we have ever achieved, showing us the shadow cast by space-time itself. Even more massive is the supermassive black hole at the center of the galaxy, Messier 87, known as M87 star. With a mass of about 6.5 billion solar masses, Its Schwarzschild radius stretches to roughly 1.9 times 10 to the 13 meters, or about 120 astronomical units, far larger than the orbit of Pluto. The Event Horizon Telescope imaged M87 star in 2019, revealing a bright, asymmetric ring of light around a dark shadow, with a jet of plasma shooting outward at nearly the speed of light. The ring's diameter is about 40 micro-arcseconds, and the image has remained remarkably consistent in later observations from 2018, with only a slight shift in the brightest part of the ring due to the turbulent motion of the surrounding gas. These images are not dramatic spectacles, but quiet testaments to the steady curvature of space-time on the grandest scales, where billions of solar masses have settled into the simplest possible configuration allowed by physics. There are also hints of intermediate mass black holes, with masses between about 100 and 100,000 solar masses, though they remain harder to confirm. Some may form in dense star clusters through repeated mergers, or perhaps from the direct collapse of massive gas clouds in the early universe. And then there are the theoretical primordial black holes, tiny objects that might have formed in the extreme density of the first moments after the Big Bang. These would have masses ranging from tiny fractions of a gram up to thousands of solar masses, depending on when they formed. And while none have been definitively detected, they remain an intriguing possibility that could help explain some of the dark matter in the cosmos. We label these ideas as speculative because direct evidence is still lacking, but they fit comfortably within our current understanding of how space-time can curve under extreme conditions. As we drift closer in our minds to the vicinity of a black hole, let us consider the effects one would experience, always described with the calm precision of science rather than any sense of alarm. Gravitational time dilation becomes profound near the event horizon. A clock placed just outside the horizon would tick more slowly compared to one far away. For an observer watching from a safe distance, time near the black hole appears to slow to a crawl. If you were to hover at a distance where the gravitational pull is strong but still manageable, you might experience hours passing, while years or even centuries slip by for distant friends. This is not science fiction, but a direct consequence of the metric describing space-time around the mass. Light itself is redshifted as it climbs out of the gravitational well, its wavelengths stretching longer and its energy fading, so that what begins as visible light might arrive as radio waves by the time it reaches us. Tidal forces caused by the difference in gravitational pull across an object would stretch anything falling toward a stellar mass black hole into long strands before it crossed the horizon, a process poetically called spaghettification. Yet for a supermassive black hole like Sagittarius A star or M87 star, the tidal forces at the horizon are so gentle that a hypothetical traveller could cross without feeling any immediate discomfort, only to encounter the increasingly extreme curvature deeper inside. These effects are not violent in description, but rather illustrate the smooth, inexorable way space-time guides all paths. We have also observed black holes through the ripples they send across space-time itself. Since 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its partner Virgo and later CAGRA, has detected dozens of mergers between black holes. The very first event, GW150914, involved two black holes of about 36 and 29 solar masses merging into a single black hole of about 62 solar masses, releasing energy equivalent to 3 solar masses in the form of gravitational waves. Those waves, tiny distortions in space-time traveling at the speed of light, stretched and squeezed the arms of the detectors by a fraction of the width of a proton over 4 kilometers. The signal arrived as a gentle chirp, rising in frequency as the black holes spiraled closer, then ringing down as the final object settled. Later events have included mergers of black holes up to about 140 solar masses each, and even one in 2023 that produced a final black hole of around 225 solar masses. Each detection is a whisper from across billions of light years, confirming that black holes do merge and that space-time can carry the news of those mergers in the most delicate oscillations imaginable. These waves are not loud announcements, but the softest possible signals of cosmic change, detectable only with instruments of extraordinary sensitivity. Another fascinating aspect is Hawking radiation, a theoretical prediction made by Stephen Hawking in the 1970s that combines quantum mechanics with general relativity. In the vacuum of space near the event horizon, pairs of virtual particles constantly flicker into existence and annihilate each other. If one particle falls across the horizon while its partner escapes, the escaping particle can become real, carrying away a tiny bit of energy and thus reducing the black hole's mass. Over enormous timescales, this process would cause a black hole to evaporate. For a stellar mass black hole of 10 solar masses, the evaporation time would be on the order of 10 to the 67 years, vastly longer than the current age of the universe, which is about 13.8 billion years. For supermassive black holes, the timescales stretch into 10 to the 99 years or more. We label this as a theoretical process because we have not yet observed it directly. It remains a beautiful implication of our current best theories, suggesting that even the most permanent-seeming objects in the cosmos are not eternal, but will eventually fade away in the most gradual manner possible. The radiation itself would be extremely faint and cold for large black holes, with temperatures inversely proportional to their mass. So a solar mass black hole would have a Hawking temperature of only about 6 times 10 to the negative 8 Kelvin, far colder than the cosmic microwave background. As we explore these ideas further, let us reflect on the broader context black holes provide for our understanding of the universe. They sit at the centers of galaxies, influencing the orbits of stars and the flow of gas that fuels star formation. In active galactic nuclei, the accretion around supermassive black holes can produce enormous jets and bright emission across the electromagnetic spectrum, yet even these phenomena unfold over millions of years with a stately grace. Gravitational lensing by black holes can magnify and distort the light from background galaxies, creating Einstein rings and multiple images that astronomers use to map the distribution of mass in the cosmos. Every observation, every detection adds another layer of quiet confirmation that general relativity describes the gentle curves of space-time with remarkable accuracy, even in the strongest gravitational fields we have yet encountered. We can also consider how black holes connect to the larger story of cosmic evolution. In the early universe, the first stars may have been hundreds of times more massive than today's stars, collapsing quickly into the seeds of supermassive black holes that then grew by accretion and mergers. Some models suggest direct collapse of massive gas clouds without a supernova stage, bypassing the stellar phase entirely. These processes helped shape the galaxies we see today, including our own Milky Way, where Sagittarius A star has likely been growing for billions of years. The presence of black holes does not disrupt the peaceful order of the cosmos. Rather, it is woven into that order, helping regulate the flow of matter and energy on galactic scales. Let us pause here and consider the information paradox, another area where theory meets its limits. According to quantum mechanics, information cannot be destroyed. Yet, if a black hole evaporates completely through Hawking radiation, what happens to the information that fell into it? The radiation appears random and carries no record of what formed the black hole beyond its mass, spin, and charge. This apparent loss of information challenges our understanding, and many physicists are exploring ways to resolve it through ideas like holography or modifications to quantum theory near the horizon. We do not yet have a final answer, but the ongoing gentle debate among scientists shows the humility and curiosity that drive our exploration of space-time. It is a reminder that even in the most extreme regions, the universe invites us to keep learning, to keep asking questions in the most relaxed and open-minded way. As we near the end of our journey together, let us circle back to the very beginning and see how far the gentle curves of space-time have carried us. From the subtle warping around our own sun that keeps Earth in its steady orbit, to the profound wells of black holes that bend light into rings and send ripples across the cosmos, every aspect reveals a universe that is consistent, harmonious, and profoundly calm. Black holes are not voids of terror, but natural consequences of gravity taken to its logical extreme, places where space-time reveals its deepest geometry. They teach us that time can flow at different rates, that light can be trapped, yet still inform us through the shadows it leaves, and that even the most massive objects can, in the farthest future, slowly fade through quantum processes. Imagine, as you lie here relaxing, the vast emptiness between the stars, punctuated by these quiet guardians of curvature. Stars are born, live their lives, and in some cases leave behind these compact remnants that continue to shape their surroundings for eons. Galaxies spin around their central black holes like dancers around a still center. Gravitational waves pass through us constantly now that we know how to listen, carrying news of mergers that happened billions of years ago. And through it all, the fabric of space-time remains responsive, curving gently where mass gathers, guiding every motion with unerring patience. There is a profound peace in knowing these facts, in understanding that the universe operates according to rules we can describe, even if we do not yet grasp every detail. As your breathing slows and your thoughts grow softer, allow yourself to feel small in the best possible way, cradled within this immense yet orderly cosmos. The black holes we have discussed tonight are not distant monsters, but fellow inhabitants of the same space-time that holds you now, curving it in their own quiet ways while you rest. We have covered so much ground together, from the foundational insights of general relativity to the latest observations of the Event Horizon Telescope and the detections by LIGO. We have examined the numbers, the Schwarzschild radii, the masses, the timescales, with care and precision, always grounding ourselves in verified science, while noting where theory ventures into speculation. Yet none of this needs to keep you awake. Let the details settle like fine dust in a still room, fading into the background as sleep approaches. You do not need to remember every fact. The gentle narration itself has done its work by helping your mind unwind. If you are still listening, know that the universe continues its slow dance, whether we watch or not. New black holes will form, old ones will merge, space-time will ripple and curve, all in its own unhurried rhythm. And here, in this moment, you are part of that same fabric, your own atoms tracing gentle paths through the curvature created by Earth's mass. There is comfort in that unity. As we conclude, take one more slow, deep breath. Feel the relaxation spreading from your toes to the top of your head. The most relaxing facts about black holes and the gentle curves of space-time have been shared, not to fill your mind with wonder that keeps you awake, but to give it permission to let go. Whenever you're ready, drift off into peaceful sleep, knowing that the cosmos is a calm and consistent place, full of quiet truths waiting to be discovered in future nights just like this one. Thank you for joining me on this long, soothing exploration. May your rest be deep and restorative, and may you wake refreshed, perhaps with a lingering sense of the vast, gentle space-time that surrounds us all. Good night and sleep well.